Hello viewers, welcome to the massive open online course on engineering mechanics. Today we will cover the unit 2 of module 3. Unit 2 is on equivalence of systems of forces and moments, and this is a part of the module 3, that is equivalent force system. Now, already in the unit 1 we have discussed what is the relevance of this equivalence of force and moment system. Now, a system of forces and moments are dealt with in any engineering problem. We come across these rigid bodies where these force and moments are there applied on the particular body. Now, these are very complicated. So, we are interested that what is the total force and moment exerted on a rigid body. So, in that case we are interested to get a simple representation of the system. Now, for this simplification we have to do by the concept of equivalence of systems of forces and moments. So, in today's session we will cover the following things, that is what are the conditions for equivalence of two systems of forces and moments, and how to determine whether the systems or moments are two systems or moments are equivalent, and how to represent a system of forces or moments by a force and a couple, and how to represent concurrent forces by a force, how to represent parallel forces also by a force, then how to represent a force by a force and a couple, then how to represent a system by a simpler or equivalent system, and lastly how to represent a system of forces and moments by a range. So, these are the things we are going to cover. Now, the first thing is, what is system of forces and moments? Actually, it is simply a set of forces and moments on a rigid body. When a rigid body is subjected to system of forces and couple moments, it is often simpler to study the external effects of the body by using the force and couple moment resultant. That means, a system of forces or moments are working, we want what is the resultant. So, rather than dealing with the all the forces and system, a system of forces and moments, we are interested how to represent it by a simpler system. So, this system, the force and couple moment system acting on a rigid body will be simplified by moving the forces and couple moments to some arbitrary point, and thus the system can be reduced to an equivalent system of resultant force and resultant couple moment. And why this is important? This is very much useful when we analyze the equilibrium of rigid bodies. Now, the next we want to discuss that what are the conditions for equivalence. Suppose two systems are there, system of forces and moments, how to determine whether they are equivalent or not. So, there are two conditions are there. First condition is, that is here we are shown that system 1 and system 2. So, they are equivalent if sum of the forces are equal, that means sigma f for system 1 will be equal to the sigma a for system 2, sum of forces are same. Another second condition is, sum of the moments about a point P are also equal. So, M P is all the moments about P. So, sigma is the summation of all the moments about the point P for system 1 is equal to sum of the all moments about P about system about a point P for the system 2, these are equal. If these two conditions are satisfied, then only we can tell that these two systems are equivalent. Now, here one illustration is there, that here we have shown a rigid bodies, two systems. In the first figure, that is system 1, on this rigid body, same rigid body, that two forces are acting, F A and F B. and a moment is applied, mc is the moment applied on this rigid body. This is the system 1, and system 2, a single force Fd is applied and two moments Me and Mf are applied on this. Now, we want to know what is the condition for equivalence. So, what we will do, the first system two forces are there. So, summation of sigma of, that means summation of all the forces for system 1 will be equal to the summation of all forces of system 2. So, in system 1 the forces are Fa and Fb, and the system 2 the force, only force is Fd. So, Fa plus Fb equals to Fd, and second condition will be the total moments. That means, the here in the first system mc is the moment, and due to these forces Fa and Fb there will be a moment about some point p. So, let us, so what will be the expression, let us see in the next slide. So, already what we have told that sigma f for system 1 and sigma f for system 2 are same. So, Fa plus Fb equals to Fd, and for moments what we have to do about point p for the first system we want to find out. So, how we will do, what is the moment arm. So, for force Fa the moment arm is Ra, this vector Ra, and for force B the moment arm is this Rb. So, if we know this vectors Ra and Rb, so Ra cross Fa is the moment due to force Fa about point P, and for Fb the Rb cross Fb equals to that is the moment due to force Fb, and mc is the direct that moment is given. So, these three will come in the system 1. Similarly, in system 2 also only force is Fd and this moment arm is Rd. So, Rd cross Fd is the moment due to about P or moment due to Fd, and other moments are there. So, all these three moments will be there. So, in the next expression we will show that mp1 equals to mp2. So, Ra cross Fa, what I have told, Ra cross Fa plus Rb cross Fb plus mc, this is the system 1, and system 2 is Rd cross Fd plus Me plus Mf. So, if these two conditions are satisfied, and then we can tell that these two systems, system 1 and system 2, then the system of forces and moments are equivalent. Now, we can extend this another from this condition of equivalence, that is, suppose if these conditions are satisfied, that means this sum of forces for system 1 and system 2 are equal and sum of the moments are equal, then the sum of the moments about any point also will be equal. If it is satisfied for a point P, then the moment about any point also will be satisfied. So, that we can prove. So, here, so what we have to prove? Let us see, already we have shown a point P. Now, we take a new point P dashed. So, here we have to prove that MP dashed, sigma MP dashed 1 and sigma MP dashed 2, they will be equal. So, this is the thing we have to prove. So, for that what will be the expression we have to prove? Our MP dashed will be the, what are the forces and moments for the first system? In the first system Fa, Fb and Mc. So, these two forces we take the moment about the point P dashed, and Mc is already there, and Rd dashed is the from new point P dashed, the distance moment arm to Fd. So, the moment due to that Fd we can find out, and Me and Mf. So, this condition we have to find out. So, let us start with this expression, then we will show that these two expressions are same, that means left side equals to right side. So, we start with this expression, then we will prove that both sides are equal. So, here what I have already told you, that a new point P dashed is taken, and so from the new point P dashed, the Fa and Fd, these position vectors are Ra dashed and Rb dashed. So, about this point we can take. So, what is the relation between Ra and Rb? So, this position vector from P dash to P is the R vector, position vector. So, this R A dash and R, R B dash and R B, R D dash and R D can be related by the following expression, that is R A dash equals to R plus R A, R B dash equals to R plus R B, R D dash equals to R plus R D. So, this expression if we put in the that expression which we have to prove, then R plus, in case of R A dash we put R plus R A cross F A. Again I can show the earlier expression, this expression we are trying to show, that is equation number 5. Here in place of R A dash we are putting R A plus R, R B dash we are putting R B plus R, R D dash we are putting R D plus R. So, then we get this expression. Then what happened after some simplification, we get that R cross sigma F for system 1 plus M P sigma of M P 1 equals to R cross F 2 sigma F 2 and M P sigma M P 2. So, in this expression we can see that R F 1 sigma F 1 and sigma F 2 for point P, it is already proved, it is already there. So, the F 1 and sigma F 1 and sigma F 2 are same, and it is multiplied by the same quantity R. So, first first terms of left hand side and right hand side are same. Then second terms, this is also already proved for point P. So, M P 1 and M P 2 also same. So, this way this equation is same. So, the starting condition, that means about any point P dash, the expression which I have got, it is proved. That means about any point these moments will be same. Next, we will apply this system of the conditions for equivalence. Let us take one problem. Here 3 systems are there. In the system 1, a 50 Newton force at origin along the y direction is there, it is applied. In the second system, a 50 Newton at the middle, the total span is 1 meter, and in the on the right side from O, the origin O, 0.5 meter distance, the 50 Newton force is applied in the y direction, positive y direction, and a moment is there 50 Newton meter, that is in the clockwise direction. And in the last system 3, this at the end of the bar there is a 50 Newton force and a moment is there, that is also clockwise. So, it is a negative moment. So, now we have to examine whether these 3 systems are equivalent, or even suppose all are not, which 2 systems are equivalent, that we have to see. So, what we will do? Our approach will be, we will test these 2 conditions, that is some of the forces are equal and some of the moments are equal about a point, that you have to check. So, first thing we are going to do, sigma F 1, sigma F 2, sigma F 3, for the 3 systems we determine, and we see that in all the cases 50 Newton force is there, in the 50 Newton force in the y direction is there, positive y direction. So, they are equal. So, first condition is satisfied, that all are equal. So, next condition is for moment we have to see. So, moment for the first case, if we see the figure, just we will go to the earlier figure, then it will be clear. In first case, just see, when you take moment about O, 50 Newton force is passing through O. So, it has its moment is 0. In the second case, the moment arm is 0.5 meter, 50 Newton meter. So, 0.5 into 50 Newton is the moment, and another moment 50 is there. So, this 50 Newton force creates a positive moment, because it is anti-clockwise, and 50 Newton meter already the moment is there, that is negative, because this is clockwise. So, they also cancel each other. And the third one, we see that at the end of the bar 50 Newton force is there. So, this 50 Newton force into 1 meter. So, 50 Newton meter will be the generated and 50 Newton meter already. So, it is positive direction and third one is also in the negative direction 50 Newton meter as it is clockwise. So, they cancel. So, in the calculation we will see all the moments are first and third will be 0 and middle one second one will be 25 kilo Newton meter. So, thus we can conclude that for the first and second both the conditions are satisfied because moments are same, some of the moments are same and some of the forces are same. That is why system 1 and 3 are equivalent, but as the moment condition is not satisfied by the system 2, that is why system 2 is not equivalent to any of the system. Now, here one question will be asked that whether we are taking about origin O, whether we can prove this if we take the moments on from at another point. So, here we have shown that if we take at the right end, then also we will see that the system 1 and system 3 the moments are same, but for system 2 the moment is different. This way the conclusion what we have drawn that system 1 and 3 are equivalent, that is valid. Now, we are going to a problem 2, that that there is a plate and all the what are the forces applied are shown. We can see along y axis there is a positive direction 10 pound force and along x axis on the left end bottom there is 20 pound force and the right end there is a 20 foot-pound moment in the clockwise direction and at point P there is a 10 pound force. This is system 1 and for system 2 15 pound on the left hand side at the origin O and 20 pound at the other end bottom right end 20 pound on the x positive x side and 15 pound at point P in the positive x side and 25 foot-pound is at the left end left top end, that is in the clockwise direction. Now, we have to examine whether they are equivalent or not. So, our way is the approach will be that we will check the summing of this, we will check the whether the sum of the forces on the plate are same and sum of the moments about any point whether they are same. So, same approach like the earlier one we can do. For the system 1, just if we see the figure sum of the forces, just in the first figure along x axis only 20 pound force is there, that means I unit vector I, and along y direction two forces are there, one is 10 pound, another is 10 pound. P at P it is negative minus and here at positive. So, here the forces are only x direction one force is there, but y direction they cancel each other. In the second system the x direction 15 pound in negative direction and 20 pound in positive direction. So, 5 and 15 pound in positive direction another. So, on the right, on the positive direction there is be 35 pound and 15 pound in the negative direction. So, 35 minus 15 equals to 20 pound on positive direction. So, let us see these two systems how. So, here we see that for system 1 it is 20 pound and system 2 also 20 pound, okay, in I direction. Now, so they are same. Now, we will check the second condition, that is whether the moments about any arbitrary point is equal. So, the sum of the moments we take here about O. So, again we go to the figure. So, here O is the origin, about that we can see that in the first system the 20 pound on the left hand side and 10 pound along the y direction, they are passing through the origin O, that is why the moment term is 0, that is why they have their moment is 0, they have no contribution in creating moment. Only 10 pound on the upper right side. So, that moment arm is 8 feet. So, 8 feet into 10 feet equals to 80 feet. So, this is in the clockwise direction and already 20 foot-pound is already there. So, these 80 and 20 will be 100 foot-pound in negative direction. And in the second case, we can see that again through the origin 15 pound and 20 pound are passing. So, only force creating the moment is 15 pound and moment arm will be the height 5 feet. So, 5 feet into 15 equals to 75, and with that 25 foot-pound in the negative. So, both are in the clockwise direction, though they are negative. So, this is 25 into 8 into 15 equals to 120 and here 25. So, let us see what is the figure. So, here we can see that all the calculation for the system 1 it comes 100 foot-pound K, that is in the moment direction is in the z direction, and second case also minus 100. So, thus the two systems are equivalent because some of the moments are equal and some of the forces are equal. Next is here now question is why we are want to find out the this system of forces and moments, whether why we want to know whether they are equivalent, because from the statics point of view it states that whether the system exerts the same total force or total moment about any point. This we are interested because this is also for statics this is will be required for analyzing the equilibrium. And in dynamics also what will be the if the systems are equivalent, then what happened, we can model it the rigid body, same type of motion will be there. If the same type of systems of forces and moments are there or the systems are equivalent, then upon applying this system of forces and moments on a particular object for both the system, same type of motion of the rigid body we will get. That is why we are interested in this. So, another problem we will see here also determine whether the systems are equivalent. Here two forces are there in the two systems are there where all these forces and moments are there. FA is the force, FA, FB, moment M, FC, FD. These are the 5 quantities force and moments will be seen in the next figure. So, system 1, that is FA, FB, 2 forces and 1 moment is there, and positions are also shown for the second force FB 6, 0, 0 and moment M and FA, and in the second case force FD at the point of application will be, coordinate of the application is 6, 3 meter, and at the origin there is a force FC. Now, we have to see whether they are equivalent. So, our approach will be that we will check again the two things, whether summing of the forces, whether they are equal for the two systems, and summing of the moments about a point, whether they are equal. So, if these conditions are satisfied, then we can tell that these systems are equivalent. So, now the solution, first thing is for system 1, the forces are FA and FB are, if we add, because already values are given, if we add this thing, then we will get this 20I 15J minus 5K. For system 2, it is again coming 20I 15J minus 5K. So, the sum of the forces are equal. Next condition is whether moments are equal or not. So, we have to take all the moments. Now, if we go to the figure, for the first figure, now we can see that force FA passing through O, and we are taking moment about O. So, this FA moment due to FA is 0. So, only force is FB, and FB's coordinate is 6, 0, 0. That means, 6i 0j 0k, 6i plus 0j plus 0k, we are writing 6i. This is the position vector and force is already given in the beginning of the problem. So, then we can do the cross product r cross f, by that we can find out the moment, and already a moment is given, m is also given. So, by from this we can find out the moment of m1, sigma m1. So, here 6i already what I have shown, 6i cross fb plus m is given. So, those values if we put, so 6i, so I is only 6 and j and k components are 0. So, this is the position vectors component, and 35, 10, these are the component of the fb force. So, and m is already given in the beginning of the problem. From this we can find out the moment for the sum of the moments for system 1. Next we will go to the system 2. System 2, let us go to the figure and see how the moments are calculated. Here we can see that the force F c passes through the origin O. So, as it is passes through origin O, moment about O is 0. So, only force creating moment is F d. So, its position vector is 6i plus 3j plus 3k cross F d. F d's value is also given in the beginning of the problem. So, by this cross product we can find out the moment. So, let us see in the expression. So, here 6i plus 3j plus 3k cross F d. So, here we are doing this thing, product we can find out I j k 6 3 3 and F d's components are 10 20 minus 10. So, it is also coming. So, this again is equal to the m 0 m o about for the system 1. So, m o sigma m o 1 and sigma m o 2 are same, that is why, and also forces are same, sigma f 1 and f 2 are also same, that is why these systems are equivalent. Now, the system 1 consists of, so here we can see that in the system 1 it consists of 2 forces and 1 couple, but system 2 consists of 2 forces. So, system 2 is much simpler, yet the two systems are equivalent, exerting the same total force. So, the system 1 acts on an object and the total force and moment same as system 2. So, we can see that we can find out. Now, the question is, so the system 2 is simpler than the system 1. So, now we can see that whether we can find a much simpler system, equivalent system than system 2. So, that will come gradually. Now, so in equivalent system, representing system by equivalent system, what is the relevance of this? If we are interested in total force and total moment exerted on an object by a given system of forces, we can represent the system by an equivalent one, because these are all applicable for the rigid body analysis. Deformable body, actually how the forces are distributed, that is very important, but in rigid body we assume that there is no deformation. So, we are interested in the total force and moments, and we find out all the analysis for equilibrium and dynamic analysis, everything. That is why we want the equivalent system, and we mean that instead of showing actual forces and couples on an object, we would show different systems that exert the same total force and moments. Already we have shown that a system of forces and moments, there are other equivalent systems are there and which are much simpler. So, we can replace a given system by a less complicated one to simplify the analysis, because if this representation can be one equivalent system, if we can find out which is much simpler, then analysis will be much easier. That is why you are interested in representation of system by equivalent systems. Now, the question is any arbitrary system. In the system 1 we have shown there are F1 to Fn different number of forces are acting on the rigid body, and there are different moments are acting on the rigid body. Now, we want whether this system 1 can be represented in terms of a force and a moment. So, in the system 2 force and a couple or force and a moment. So, this we are interested how to represent that. So, again the condition is say sigma of F2 equals to sigma of F1. So, in the first second case, that means the representation, that means we are replacing the system 1 by an equivalent system which is shown in system 2. That means these forces and moments are replaced by one force and one moment. Now, equivalence, from the equivalence conditions, what will happen? The F1 to Fn, sigma of F1 to Fn equals to the F. So, just you see sigma F equals to sigma of F for system 1, and another condition is this all the forces, that is moments of all the forces about P we are interested. So, that can be represented by one moment in the second system, equivalent system. So, the second condition is MP2 equals to MP1. So, the MP2, that means second system equivalent system M equals to sigma of all the moments in the system 1. So, these conditions are satisfied if F equals the sum of the forces in the system 1 and M equals the sum of the forces. This way we can represent a system of force and couples by a simpler system. Now, how to represent a force by a force and couple? This is, and we are interested. A force F p acting at a point P. Now, it can be represented by a force at a different point Q and a couple M. So, first system 1 is given. We want such a system where the point of application is Q and along with it there will be one moment. So, we want to find out this what will be the values of this F and M. How we will do? The same thing, that for the both the system 1 and system 2 we take the sigma of the or the summation of all the forces will be equal. So, for this system 2 the resultant system 2 is represented by one force. So, that is F. So, that F equals to system 1 the force is F p. So, they will be equal. System 2 the moment is M, and in the system 1 already system 1 this force will be due to F p, there will be a moment. So, that from Q, about Q, just see. So, about P if we want the force. So, M equals to R cross F, the first system R cross F, if we find out, then that is equivalent to the moment will be there in the first system, the system 1 the moment will be R cross F p, and second system the moment is M. So, both will be equal if these systems are to be equivalent. Thus, this is the condition for this thing if we want to represent, that means this one, that means first system we represent in terms of like a force and moment given in system 2, then the conditions are, that is F equals to F p and M equals to R cross F p. This way you can find out. Now, another case is when concurrent forces are there, whether we can represent the concurrent forces by a single force. So, here F1, F2, F3 all these forces are working, they are concurrent, they are passing through a single point, and whether we can represent it by a single force F which is also passing through that same point. So, what will be the condition? already the equivalence systems conditions we will put here. That means, first system all the sum of the forces, second system the sum of forces equals to F, and first system sigma F1 equals to F1 plus F2 plus F3 plus Fn, and as there is no moment. So, there is no question of moment. So, this is the condition if the concurrent forces are there, if we want to represent it by a force. So, F equals to, so sum of the moments about P is equals to 0 for each system. So, the system of equivalent, if the two forces equals the sum of the forces, then it is sufficient for equivalence. Thus, we can find out. Another condition is if parallel forces are there, if we want to represent by a single force, that is also we can do, and this we will show in a example bit later. Here we want to represent a force by a force and couple. So, already we have proved this thing, now we are solving one problem. So, system 1 consists of a force F A, that is 10 I plus 4 j plus minus 3 k pound acting at A, and A's coordinate is 4, 2 feet. So, represented by a force acting at B and a couple, which already we have proved. So, you want to represent the force F by a force F A by a force F at B and a couple M. So, what we do, that sum of the forces for these two systems will be equal. So, sigma F2 equals to sigma F1. So, this is the, here what will be the sigma? In the first case this is F A, and second case the F A is already given. So, F is the second system, that is here we are showing F. So, this F will be system 2, the sum of force is F, and system 1 sum of forces will be F A, that is already given value 10 I plus 4 j minus 3 k pound. Now, sum of the moments again we have to find out. So, first we will find out the moment arm from B to A. So, you from A position vector from A to B we have to find out, that means coordinates of A minus coordinates of B, from that we can find out 4 minus 8, 4 minus 0, 2 minus 6, from that we can find out. So, RAB, that means moment arm we can find out the So, the about point B we can find out the moment of force A equals to that moment arm I j k, the moment arm component are minus 4, 4, minus 4, which I have shown in the earlier thing, minus 4, 4, minus 4, these are the three components of RAB, and force components are 10, 4, 3. So, by this determinant we can find out these values, and so, and sum of the moments about B must be equal. So, now this MB2 equals to MB1. So, in the second system the moment is M, and first system already we have derived RAB cross FA. So, if we put that, so we can find out the moment. So, the particular system of force can be represented by a force and a moment, and that force is applied at a different point, and what will be the applied, if the coordinate is given, then we can find out what will be the moment. So, this we have found out, force will be same and what will be the moment. This way we can represent a force by a force and couple. Now, in this case we have not didn't specify the point of application of couple M. Actually, this is the moment of the couple is a free vector, that is why we do not mention. If it is only applied on a particular body, that is the condition for which we are considering the equivalence on a particular body. So, that force and moment should be applied on that particular body, that is the condition, otherwise this moment can be applied anywhere, it is a free vector. Another problem we are going to solve, that is how to represent a system by a simpler equivalent system. Now, here we can see that here is a system where two forces are acting along the x axis at 3 meter distance from the origin, and another is 5 meters distance from the origin. This force amount of the force is 30 kilonewton, and directions are also given, and at the end of the pipe, it is a pipe, at the end of the pipe another moment of 210 kilonewton meter is applied. So, how we will proceed? So, first what we do, that particular, again the system is given like this. Now, one equivalent system we want to find out. This equivalent system is just one force and one moment, and we have decided that this force will be applied at the origin. So, we can represent system 1 by a force acting at the origin and a couple m. This is the first thing we will do. That means, one system 2 we will find out such that one force will be applied F and moment which is equivalent to that earlier system, and then we will place a that particular F along the axis along the x axis of the pipe, and see the another equivalent system, system 3. That means, only force is applied and which will be equivalent. So, we have to find out what will be the distance d. So, how we will do? First thing is system 1 and system 2 will be, that means this all these forces and moments will be represented by one force and one moment. So, sigma of F2 equals to sigma of F1. So, let us see the figure once more. These are the forces. So, 30 kilonewton and 20 I 20 J kilonewton, these are the two forces, and 210 kilonewton meter. These are the three things. So, these forces we have to add to find out the one single system, that is system 2, where the force is F and moment is m. So, what we do? F for system 2, F summation of forces is F, and already two forces in system 1 are added and we get this thing. And second condition is that system 2 moment is m, and that is the sigma of all the forces and moments in the system 1. So, if we find out, that is coming around 400 kilonewton meter. Now, this is the system 2, we have equivalent system 2 we have found out. Now, the question is, because we have made a equivalent system, that is system 2 is equivalent to system 1. Now, we want to find out another simplest system, that is system 3, which is also equivalent to system 2. System 2 means it will be equivalent to system 1. So, in system 3 simply one force F is applied at a distance d. So, if you compare for the system 3, the moment will be 50 kilonewton, because just we see the figure. So, here the force F at distance d. So, that moment we have to take, that moment is equals to the moment of the system 2, that is already found out, that 400 kilonewton. From this we can find out the distance d. So, that way we can see that these three systems are, already we have shown these three systems are equivalent. The third system is most simple, only one force is applied at distance d, which will be equivalent to system 2 and system 1. So, this way you can represent. Now, in system 3, why did we assume that the point of application of force is along x axis? Because here we have to, in order to represent the system 2 by a single force, we needed to place the line of action of the force, so that the force would exert a 400 kilonewton counterclockwise moment. So, to move that to that moment is there, that you have to cancel, that way only one force will be equivalent to that. So, that way we can make a very simple equivalent system. Next, another problem is here how to represent a system by a force and couple. So, here a system 1 is there, FA and FB, two forces are there and one moment MC is there. We want to represent by a force F acting at P and a couple M. So, we have to find out F and M. So, again we have to, what will be the approach? Again sum of the moments about the point you have to find out and obtain the simpler equation assuming the thing. So, some of the force and couples of two conditions of equivalence that we will do. So, let us do one by one. First thing is, first condition is the system 1 and system 2. System 1 is the given system. System 2 is we want to find out that at point P a force will be given and a moment will be applied. Now, just see once more. So, obtain simpler equation by assuming moments about P, because the moment due to F about P is 0. Now, here the system 1, this is the system 1 and this is the system 2. So, sum of the forces here, what are the forces? F A, F B, here the F C. So, F because we want to find out F and M equivalent system. So, F equals to F A plus F B, F A and F B are given and moments about for the system 2 and system 1 we have to find out. For the system 2 we want that single moment, that is M. So, that M will be equals to all the sum of the moments for system 1. So, in system 1 if we go again, so two forces are there, F A, F B, two forces are there. So, the moments due to these two forces and one moment M C. So, summation of all these will come here. So, this first term, the first term is this system 1, F A, F B and the M C. So, if we add these three, then they will be equal. So, from this thing we can find out from this condition. So, M, that means for the equivalent system what will be the moment or couple, we can find out from there, moment of the couple we can find out from here. Now, here the question is, this example demonstrates that most common application of the concept of equivalent system, and in engineering we often deal with complicated system of forces and moments, and it is very convenient to be able to represent them by a single force and a couple. So, which we have done there, although the system 1 in this example is not very complicated, but our procedure for determining will be remain same, and thus for the equivalent system F and M we can find out whatever may be the system, and it is irrelevant how many number of forces are there. Next, another problem already we discussed, that if there are a number of parallel forces are there and we want to represent by a single force, then how we will do? That also we can do by using equivalent force system. This system 1 consists of 3 forces and 20 pound, 30 pound and this 10 pound, and directions are given in the figure, and we want that what will be the, if we want a equivalent system where a single force can, by this all this system can be represented by a single force. So, what will be done? We want that this force here, we want the what will be the force and what will be the point of application, and this point of application we want where it will be in the xz plane. In xz plane, what will be the point of application? So, for this we can determine the condition of forces and moments we can apply, and then also for the moments also we can apply, and from this we can do same rule, and position actually unknown to us, that we can take here the sum of the forces for both the systems. That means, if the equivalent system has a single force F, because already earlier figure we have shown that earlier system is equivalent of that system is this one, where F actually replaces all those forces. So, sigma F2 equals to sigma F1, sigma F2 is second system, the only force is F, and for the first system whatever forces are there, given forces, if we add, we will get the force F. Now, we have to go for about any arbitrary point, we have to take the moment. Moments will be equal, we know, for the two systems. So, let us consider the coordinate of the point P is x, y, z, but as it is a xz plane, this y equals to y will be 0, we will put this y will be 0. So, m2 0 and m0 sigma m0 for system 2 and sigma m0 for system 1, these are shown here. So, if we put, let us see how we will take the moments for the system 2, that F is there and point P is there. So, point P we take x 0 z, these are the 3 coordinates that we put here, and x y z we will put and y will be 0, and for other points we know first system, that is first system, we know all the coordinates. So, r cross f in that way in vector form, if we put cross means I j k 6 0 2. So, if we put all these things and get an equation, and by simplification of this thing we can find out x and z, because as it is in xz plane, y is automatically 0. So, there we will put y equals to 0. Now, question is, in this example xz coordinates of P is determined in a simpler way. Even if we take the moments about any line also, then also we can find out these values, that is about x axis sum of the moments if we take, then also we can find out the value of z by equating these two, or we can, if we take the about z axis sum of the moments for system 1 and system 2, then also we can find out this value of x. Now, one important thing is that already we are dealing the representation of a system by an equivalent system, and we are trying to get a very simplest system. So, what will be the simplest system? So, here the concept of range comes. Range means a force and a moment, and that moment's direction is parallel to, moment vector is parallel to the force vector. So, if we can represent a system in terms of a range, then that is the most simplest representation. So, how it can be done? How it can be done if any force and moment is given? So, what we do, that if any force is given, then we can find out the, just see here in this figure, if the system is a single force or a single couple, or it is a force F and a couple that is parallel to F, that is range. So, this is the simplest system, we cannot simplify further. If the system is more complicated than a single force and single couple, we can begin by choosing a convenient point P and represent the system force F and a couple M. This we can do. Now, in this case, in case of range what we do, actually we want that suppose a force and a moment is given. So what we will do, representing this system by a range, the following steps are followed. One is, first you determine the component of the moment along the force and normal to the force. Next, whatever the normal component there, that has to be generated by a force, that means by the force F, which will be equal to the Mn or normal force, that means R p q cross F equals to Mn. So, two components are there. Directly in the system we will give force, one force and Mp, Mp is the parallel to F. So, this Mp and F creates the actually it creates the range, but the given force may have that another normal component. That normal component has to be created by the force. So, created by the force. So, we have to find out such a position where if the force is applied, we will get that thing. So, actually this thing we will explain by one example. A system consists of a force and a couple. Force is 3I 6j plus 2k and moment is 12I 4j 6k. Now, we have to represent it by a force, by a range. Range means a force and a moment which is parallel to the force. So, how to do that? First thing is, what approach is, the range is the force F and component of M, actually this is the given force, given moment parallel to F, and that we call Mp, and normal component is Mn. So, how to find out? First what we do, F is given. So, what is the unit vector in the same direction? So, F by the vector by the magnitude. So, we get the unit vector. Now, we can calculate that moment vector, what is the component along the, that means parallel along the force F, the same direction parallel to the F. So, Mp equals to E dot M into E. So, this way we can find out the component of the moment which is parallel to the force. So, once you, for the total moment is M and total moment is M. So, if you find out Mp, so if you subtract that thing from that vector, you will get the Mn, that means normal vector you can get. So, now we have to find out that this normal vector is not given, we have to generate, we have to find out such a point where this F should be applied, x, y, z we take, and in the x z plane if we take, that is x 0 z if we apply, then then this r, then the moment vector r o p from the earlier position, r o p origin from origin, r o p cross f, if we find out, then we will get this expression. Here the unknowns are x and z, because we do not know where the point of application of f. So, we have some condition that this should be equal to the normal component. Normal component already Mn we have found out. So, this quantity will be equal to this r o p cross f. So, if we equate these two equations, we will get and simplify this thing, then we will get the coordinates of x and z, and thus we can find out where the force F has to be applied, so that just force and one force, that means range, force and one moment, that is parallel to that force will be sufficient for creating the given force and moment. So, this way you can find this is the simplest representation. And why this we place the point P on the arbitrary x 0 z in the xz plane. The objective is was to place the line of action of force of the range so as to satisfy the condition that moment of F about O is equal to Mn. So, Mn we have to generate, that is why we took the line of action we have to for finding that we did thing. So, other way also we can find out. So, today we have covered the few things. One is the two systems of forces and moments are equivalent if the sum of the forces are equal and the sum of the moments about a point are equal. To check whether two systems of forces and moments are equivalent, the two conditions for equivalence for the system are checked. A complicated system of forces and moments acting on an object can be represented by simpler system to gain a better intuitive understanding by their effects of the object. And a force can be represented by a force and a couple using equivalent system. A system of, we have shown that a system of concurrent forces can be represented by a single force applying condition of equivalence. Then we have shown that a system of parallel forces can be represented by a single force by applying the condition of equivalence. Then we also shown that a force can be represented by a force and a couple using condition of equivalence. A system of forces and moments can be represented by a simpler equivalent system using condition of equivalence. And lastly, we have a system of forces and moments can be represented by a range. So, here we have discussed all these things, and the main books which can be consulted for this subject. So, these are here are few books, Bradford Fowler, Bella Sander, then B.R. Johnston, Hibbeler and K.L. Kumar, many other books are there. So, can be consulted, which can be consulted. So, thank you.